Hello everyone. Welcome to our webinar today. We'll still give people 1 or 2 more minutes before we really get started. But thanks to those who've already joined us, our panelists as well. Yeah, we'll say more in just a few minutes. Thanks. Okay, so welcome everyone. I see we have a good number already. Hopefully we'll pick up a few more while we're just introducing and opening the session. So thanks to all those who've joined. We have a wonderful session on microplastics and nanoplastics today, hoping to bring you some knowledge, some information on the topic, and maybe give ourselves some inspiration for any future webinars or future topics to work on. My name is Oliver Wotton from Unitar. I work in the Chemicals and Waste Management Programme, and I look after our nano portfolio. It's our great pleasure to put this webinar together. And again, for the second time in this series, we've done it in collaboration with the BRS conventions. So I will have a little presentation just to guide you through some of our work. But before we do that, I'll pass over to our colleague from the BRS Secretariat, Agustin Harte, who's online just to give us a few opening remarks. So over to you, Agustin, please.
Thank you very much, Oliver, and good day to everyone. I'll try to be brief, but on behalf of the BRS Secretariat, I would like to thank you, all of you, for your interest and participation on this new webinar, which focuses on micro and nanoplastics. And of course, I would also like to thank Unitar for organizing and taking the lead for preparing this webinar. So as Oliver said, my name is Agustin Hart. I'm a Program Management Officer under the Science and Technical Assistance branch within the Basel, Rotterdam and Stockholm Convention Secretariat. Just briefly, some of you may not be familiar to the Basel Convention and the work we are doing there, but in May 2017, at the 13th meeting of by decision 13/17, the Conference of the Parties of the Basel Convention requested the open-ended working group, which is a subsidiary body under the Basel Convention, to consider further work that may be carried out in relation to waste containing nanomaterials on the basis of a paper to be prepared by the Secretariat on issues related to such waste. So that's where our mandate started from. And the report on issues related to waste containing nanomaterials and options for further work under the convention was developed and made available by the Secretariat to parties and observers. And since that decision, the Secretariat has collected new information related to activities aimed at addressing issues related to waste containing nanomaterials, including case studies about the best practices relating to the management of waste containing nanomaterials, which can be submitted by parties and observers to the Basel Convention. And every submission, we always made this available through our website. So in its decision 14/8, the open-ended working group requested the Secretariat to continue the work and invited parties and observers to make available to the Secretariat by the 31st of December of 2024, so next December, any new information related to activities aimed at addressing issues related to waste containing nanomaterials, including, as I was mentioning, case studies. The open-ended working group also requested the Secretariat to organize activities to raise awareness among parties of activities aimed to addressing issues related to waste containing nanomaterials. So this is one of the webinars that we co-organized with UNITAR to fulfill this activity. And finally, the Secretariat is going to report on all the information received and the implementation of these decisions to the Conference of the Parties at its 17th meeting, which will happen in April and May next year. So if there is any specific issues or specific matters on nanotechnology, nanomaterials, and waste containing nanomaterials that you would like to share with the Secretariat, on awareness raising, on case studies, etc., you may reach out by email. I will leave my colleagues and my emails in the chat. And just to end my remarks, saying that we'll be happy to receive those informations or requests for activities by 31st of December so that we can report back to our COP. This is a series of several activities that we're ongoing, and we are eager to hear from the experts on what are the challenges dealing with nanoplastics and microplastics. So I wish you a great webinar and fruitful discussions. Back to you, Oliver. Thank you very much.
Great. Thank you very much, Agustin. Thanks for that. I will just run through a quick presentation we have on our work. We're very pleased to work with the BRS Secretariat, and I'll mention some of that and some of the other work we have done on nanotechnologies and manufactured nanomaterials. So I will just be very quick, and then we will lead into the next presentations from the experts. So just running through, we have, for example, an e-learning course. We have done this over the last 10 years or so and revised the course back in 2022. That was with our experts that we use. So one is from Vladimir Murashov from the US, a senior expert, George Kalaganis, who you will hear from later, and others who helped review. That's online, available to any stakeholder, and is free to access. For those of you that don't know, back in 2012, nanotechnology and manufactured nanomaterials was added to CEST as an emerging policy issue. And that was a piece of work that we led with OECD until 2023 at ICCM 5 at the sunset of CEST. Some of the activities that we undertook as part of this, for example, were a round of 2015 regional meetings. We did one in the Latin American and Caribbean region in Colombia. Outcomes from this included the development of a nano network for the region, sharing information on activities at global and regional levels, and the development of short and medium-term action plans. And those reports are available online. When we did similar process in 2018 with regional meetings, one of the key focuses was the WHO guidelines on protecting workers from potential risks of manufactured nanomaterials. We also undertook a variety of national projects. So this was coming from funding from the Swiss government, and we worked in Armenia, Jordan, Nigeria, Uruguay, Vietnam, and Thailand. And they all undertook similar priorities, similar activities depending on their national circumstances, but they looked into disseminating information, bringing together different stakeholders at the national level, and developing national policies and guidelines to manage nanomaterials. I mentioned CEST as an emerging policy issue. And for those of you that don't know, the Global Framework on Chemicals, which was approved or finalized last year, also had a resolution on those emerging policy issues and agreed that all existing EPIs should transition on an interim basis to issues of concern as part of the GHC. So in this sense, UNITAR and the OECD continues its work, certainly until 2026 with the next international conference, when we'll assess progress and future potential activities. But of course, we don't just coordinate with OECD, we do that with a wide range of stakeholders, and indeed here, working with the BRS Secretariat and trying to support work under the Basel Convention. So that is a quick introduction from me, UNITAR and UNITAR's role under the GHS. So with that, I would like to just pass over to our next presenter. I'll ask you, Bernd, to just introduce yourself very briefly, and then over to you to share your screen and go through your presentation. Then we'll follow through to the next presenter, and I'll ask each at that time to briefly present themselves. So over to you, Bernd. Thank you.
Okay, now welcome everybody also from my side. Now, my name is Bernd Nowak. I'm working at the Swiss Federal Laboratories for Material Science and Technology, and here in the group, we have been dealing for many years with nanomaterials and now also with micro nanoplastics. And yeah, this was the reason that I was asked to present here shortly. And I gave it the title, The Plastic Continuum from Litho to Microplastic, and finally to Nanoplastic Release and Exposure Considerations. So I think you're seeing the correct mode. So this full screen.
Yep, looks good, thank you.
Okay, now. So what are we talking about here? The plastic size continuum. We have these macroplastics, so the litho larger than 5 millimeters. We have then the microplastics between 5 millimeter and 1 micrometer. And then we have nanoplastics, usually now considered to be smaller than 1 micrometer. So we have here a whole size continuum. We cannot just talk about nanoplastics without not considering micro and macroplastics. If we further go into microplastics, we have here, that's a collection from a beach. We have here different types. We have the primary microplastics, pellets, that are produced in industry in this form and make it to the environment. And then we have here the rest, the secondary microplastics formed by degradation of larger plastic pieces. And the link between all of these plastic size classes is fragmentation, where it goes from the litho, the macroplastic, into microplastic, and then into smaller and smaller pieces until we finally reach the no longer visible nanoplastic. So in our work, we are always trying to assess release of plastic to the environment. How do we do this? First, we need to know the material flows of plastic. So what is produced, what cannot be produced and used cannot be released. So that's always the basis of the work. Then we assess release to the environment throughout the whole life cycle of plastics. And here we make some experimental work on some what we think relevant release processes. I will also show something there. We then do a regionalization. So release of plastic happens at certain locations, trying to predict where are these locations, and then include environmental fate, so that finally, based on use of plastic in our society, we can predict environmental concentrations of macro and microplastic. And I will try to show some snapshots from this work, how we can here look at this whole release field. So the starting point is always the material flow analysis. Plastic is produced, consumed, there's an end-of-life treatment, there is trade. We have so far considered a lot of different polymers. So these are the standard polymers like polyethylene, low and high density, polypropylene, polystyrene, EPS, PVC, PET, and so on. So a range of the most relevant polymers from a production point of view. We have also looked at tire wear, so rubber as an additional polymer. So far, we have done this for EU, Switzerland, and China, having this detailed assessment with a very high resolution in the consumption phase, because this, and they're really looking at different product categories, because this is where a lot of the plastics are actually released to the environment. Now, we looked at 9 product sectors, 36 product categories, in some studies, even more distinct product categories. So just one example with a bit surprising result. If you look at plastic consumption, so the absolute basis of our work, and that's now for Switzerland, the dynamic modeling starting in 1950 and going up to 2022 here. And in a way, the interesting fact is what we see here in Switzerland, that we have reached the peak plastic. It's related to the mass per capita. Switzerland grows quite strongly in population. It's about more than 10% per decade. So overall, it's quite constant, but related to the plastic that people actually consume, there's quite a significant reduction already that we see. So all the efforts that are made also by reducing packaging is actually visible if we look at it from a single person point of view. So this was just one example from this kind of the material flow analysis work. But now if we go to the release, and there I would like to highlight some of our work we do in the experimental work on the release, because we need understanding where does the plastic in the environment actually come from. And we focused a lot on microplastic fibers from textiles, where we look at the whole life cycle, starting with pellets, making the yarns, the fibers, and the different situations during the use phase of a textile, like washing, abrasion, outdoor use, and then landfill. And so far, everybody knows, okay, during washing, there's something released, we have all these fiber release, but that's just one step in the whole life cycle where fibers can actually be released. And we looked at a lot of different places. It already starts during production where a lot of fibers are produced. There's a lot of abrasion, there's outdoor use, in, even under landfill conditions. With weathering, one can have a lot of release of different fibers. So this would be how a fleece, the surface of a fleece shirt would look. This is what is then released during washing. So these microplastic fibers, and that's what everybody studies, but there's much more that this fleece can produce. If you have abrasion, you form, for example, much smaller fibers. You see this kind of, it's fibrillation, the fibers split into smaller fibers, and then you form some very thin fibers. And if you expose it to weathering, there's a lot of other particles that can be then formed just from the textile. So just looking at this UV weathering, there's a huge zoo of particles that is formed when textiles, polyester textiles, are exposed to sunlight. So what is released sometimes are these regular microplastic fibers, those that everybody studies. Then there are several that are in the process of splitting up. You see a lot of different forms here, a lot of thin fibers that can be formed. So all the numbers that you see here, these are the diameters. The original fibers are about 12 to 13 micrometers, but you see there's a lot of much thinner fibers. There are also ribbons that suddenly, it's kind of rolled up fibers that are much thicker now than the fiber. If you would find them in the environment, you wouldn't realize that they actually come from textiles. And there's a lot of other shapes that we observed when you weather these textiles. Because what we also see here, it's now if we go from micro to nanoplastic. So we have here these microplastic fibers, definitely, yes, microplastic. We see these fibrils, these smaller fibers, still in the range of microplastics. But then you see on this filter here a lot of small dots. And the question is, are these now nanoplastics? Something that is smaller than 1 micrometer. And we also investigated this, for example, looking at the concentration now of nanoplastics by here one measuring techniques, the nanoparticle tracking analysis. And you see here with repeated washings, we find for here a range of different textiles initially, but a lot of these nanoparticles released. And then it levels off. And after some time, you cannot extract any more nanoplastics. And looking at the surface of the fiber, it seems they come from production. There's something on the surface. And after washing, the surface is more clean. So there's something released, and we first said, okay. And we had some evidence from one analytical technique that this is actually nanoplastic that is released. But then we continued the work, and now we need to say, okay, likely these are not nanoplastics, but kind of nano-oligomers. So not the polymers, but oligomers, because these particles are to a large extent soluble in ethanol. So here, the nanopet, nothing happens. But if you look here, for example, the satin sample, green is the particles in water, blue in ethanol. So you dissolve these particles, clearly showing this is not a plastic, a polymer. This is something that is soluble in ethanol, so these oligomers. And we have some analytical evidence that this is the case by this technique, pyrolysis GCMS, where here you would see in orange the signal of the PET standard. You don't see it in the top curve, which would be the sample from the textile washing. But in the textile washing, we have the same signal that we find in a methanol extract or ethanol extract of PET, which is known to extract these oligomers. So it means it even is beyond just from liter to microplastic to nanoplastic. We have one step further that then we may have insoluble, water-insoluble oligomer particles that are also present in our samples in quite high concentrations and that are also released to the environment. Okay, so in our release assessment, we base this on our material flow models. We identified and release processes. We parameterize our release model with some release factors, and we do this for macro and microplastics. So that's one example of such a model, plastic emissions in Switzerland. Now all different polymers combined. So here are macroplastic emission flows. It's a simplified model combining a lot of single flows. We also have the microplastic side, where again, it's in the middle is the kind of the different compartments in the life cycle, and it goes into some technical and then at the both sides, the environmental compartments. And we can analyze these data, for example, looking at here, releases in gram per capita per year, where we see it's mostly macroplastic, about 0.5 kilogram per year that is released to soils, microplastic, 70 grams, much less into water. So soil is the main compartment receiving these microplastics and macroplastics, and it's mainly macroplastic that are released. So here again showing this soil, about 70 grams of microplastic per person and year, released water, just 2 grams. We look at the different processes that result in these emissions for microplastic. There's a lot of consumer processes, the clothing, so the fiber release that I showed, the different colors here are the different polymers. So one sees that different kind of product categories result in very different releases of different polymers to the environment. On the macroplastic, the right side, you see the largest contributor, the littering of consumer bottles made from PET, but also the other packaging. So currently we are updating this. That's now already 5 years old. So we have now, there's much more information available about some of the release processes. And in this update, there are quite some changes, but I cannot go into this today. Then, very important, the discussion about tire wear. If we do the calculation for Switzerland, we see there's almost 1 kilogram per year and person of tire wear, which is always kind of by definition microplastic release compared to all the other polymers. So if you just look at all microplastics combined, it's completely dominated by tire wear, because tire wear abrasion happens directly in the environment. A very important point to consider in the whole microplastic discussion. So then we have the step 4, the regionalization. I don't want to go into any details, but we came up with these maps based on some proxy indicators to distribute the amount released into some smaller cells of here 100 by 100 meters. That's low density polyethylene that one sees here, a lot of use in agriculture. So it's visible high concentration in those areas where there's a lot of agriculture and in the inhabited areas. So we have these kind of maps of releases, and we use them then in the next step, combining them with environmental fate models, where then at the end we get concentration maps like this, and this is now really concentrations of microplastics in the Swiss River network based, so that's a prediction based on the use of plastics in our society, where one sees the concentrations that we predict incorporating the release and the environmental fate processes. And one example here, so that's from one river, the Aare, until the border in Basel of the Rhine, a few hundred kilometers. Blue, the modeled microplastic concentrations, and red, the modeled macroplastic concentrations. So the axis, the y-axis is normalized, the amounts are very different. But one sees very different behavior, especially macroplastic, where you have very quick release and then very quick processes that remove again the macroplastic from the river. So there's not much macroplastic actually transported out of Switzerland, except the local release, where it's different from microplastic, where there's much more of the released mass is actually exported from Switzerland with the Rhine towards Germany and finally the Netherlands. So we come to some conclusions. What I tried to show you, yes, we can model microplastic release and concentrations in the environment based on such a model that is starting with actual use of plastic in our society. And this is really the basis for the model. It's the flows of plastic through the anthroposphere. So we need to know what plastic is used in what application. When we talk about emissions, it's mainly microplastic to soil. So that's much more important than into water. There are much higher amounts ending up in our soils than in waters. And it's still waters receive much more attention. Higher wear, that's, if you look at all microplastics combined, that's the most important material. For Switzerland, we predicted 95% of all microplastic released is actually tire wear. If you look at these fibers that are also very important part of the microplastics in the environment, there's much more than just these large fibers that everybody looks at, that everybody finds in the environment. All these smaller types of fibers, they're much more difficult to analytically observe, but their concentrations are likely much higher. And it's especially that this abrasion and weathering that produce a zoo of particles, especially if you start with textiles. It's no longer that you then also just find fibers, you find a lot of other shapes and forms. And the last point, if we talk about nanoplastics, that we have to be really careful not to mix up the actual nanoplastics, so polymer particles, from oligomer nanoparticles. And with this, I'm at the end. I don't know how much time there is for discussion, so I give it then back to Oliver.
Mm-hmm. Thank you, Bernd. Very good, very good. And I see we're spot on the timing on the agenda. We were going to go through all three presentations and then open up a question and answers session. So we'll come back to you for any questions from the participants, but thank you very much. I know you've agreed for us to share your presentation, so we'll do that in a sort of a summary wrap-up message after this webinar in the next day or two, but I'll talk more about that later. We're then passing over to Natalie Tufengshi, who will present as well. So over to you, Natalie, please. Introduce yourself quickly and then go through your presentation. And yeah, thank you. Over to you.
Thank you very much, Oliver. Thank you for inviting me and giving me this opportunity to share with you some of our work and thoughts on micro nanoplastics. Thank you, Bernd, for a very interesting presentation. So I'm going to try and share my slides with you here. Let's see, hope this works. I believe. Let's see.
Yeah, coming up, and then just the full. Yep, perfect. Thank you.
Is this the right view now? Are you seeing the right view?
Yep, that's the right view. Yep.
Great. Please bear with me as I'm recovering from bronchitis, so might have to take some pauses for some hydration during the presentation. So thank you so much. As I mentioned, I'm sharing with you some work that we've been doing on microplastics and nanoplastics.
Eric Rushton. So Eric, over to you. Please introduce yourself quickly and then share your presentation. Thank you.
Sure. I hit share, hopefully. My name is Eric Rushton. I'm the Director of Toxicology and Risk Communication at LyondellBasell. It is a chemical and petrochemical company, as well as one of the world's largest polymer producers. And today I'm going to give you guys a shift away from the micro and nanoplastics and just try to give an overview of plastics to try to explain just how broad a term kind of plastics is and what it encompasses. Now, I am going to, full disclosure, I am not an expert in all of these types of polymers. I'm not an expert probably in any of these types of polymers. However, I know a little bit about a lot of it. So hopefully that will suffice for today. Let's see. So today, I'm just going to give two quick little sound bites on my company. Then we'll go into plastics versus polymers and a little bit of how you can break out some of the different plastics, talk super briefly about additives, and then kind of summarize a bit. So my company, as I said, we do make polymers. And where are we going with some of these? Well, we're trying to, make potable water delivery more realizable for a lot of areas. So stronger, longer lasting pipes, healthcare, surgical face masks, pill coatings, coating bottles, agricultural efficiency, food safety, food packaging and films, which is probably something pretty big for us, as well as stronger and lighter plastics, as well as fuel efficiency chemicals. We are recognizing that plastic waste is an issue, and we do have some sustainability ambitions to help capture that. 2 million metric tons of recycled and renewable-based polymers should be produced and marketed by 2030. For every dollar that we invest in venture funds to address the plastic waste, $5 from co-investors is realized. And there is an initiative across the industry called Goal Zero, and that is to have zero plastic pellet loss to the environment from our manufacturing facilities. We recognize that during transport, accidents can happen. There can be releases. However, the day-to-day release from plants down the drain and into the environment should be zero. We also have some climate actions and diversity actions, but those aren't really relevant for today's talk. So when we talk about polymers versus plastics, so a polymer is a large molecule made up of repeating smaller units called monomers. And plastics is a polymeric material that can be molded or shaped when heated and hardened. So plastics are a type of polymer. So not all polymers are plastics, but all plastics are polymers. Natural polymers that you have heard of possibly are starch, polysaccharides, DNA. So those are some polymers. And the dictionary definition is here, but I won't read that to you today. So where is the plastic production taking place in the world? Here you see two numbers, a dark number and a light number. The dark number is from 2017, and the lighter number is from 2021. And so North America has remained constant with about 1/5 of the world's population. Latin America producing only around 4%. The EU has seen a decrease in their polymer production from around 20 to 15%. And this has been picked up by the Middle East and by China. So China currently accounts for nearly 1/3 of the world's plastic production. and you see a small decrease in Japan, an increase in the other regions. But what type of plastics are being requested? So the global plastic production is a big chunk of that is polypropylene. And then you have the polyethylenes, PVC, some more polyethylene, and then you get to some smaller amounts coming around the side. But the global plastic production is dominated by 3 polymer types, 4 if you want to break out low density and high density polyethylene. And I'll get into some more details on these later. So what are plastics? How can we think about the plastic production? And one way is to try to think about classes. And several types of classes are listed below. They're not mutually exclusive. So something can be found in 2 of these classes. And by no means are these the only classes that can be used to break plastics apart, but they're probably some of the common ones. We do have thermoplastics, those that can be melted and reshaped without undergoing significant chemical change, thermoset, which are plastics that undergo the chemical change when heated, leading to a permanently structured form. Elastomers, which probably is a little bit self-explanatory. Biodegradable plastics. We have the bioplastics in engineering plastics. Now, thermoplastics are what we're going to be talking about most in the research and use. So what I'm actually going to do in the next few slides is I'm going to take these from the bottom and end up here at the top. So if we start with engineering plastics, these are very specialized plastics that are designed for specialized applications. So there are a number of different chemicals, polyether ether ketone, PEEK, polytetrafluoroethylene, PTFE. It's known by its trade name, Teflon. There are polyamides, polysulfides. But what is obvious from these compounds is that they are generally high strength, heat and chemical resistance, basically across them. Another one that's not on here is Kevlar, which is for bulletproof vests and used in some tires as well. But these specialized polymers tend to be used in aerospace, electronics, automotive, again, aerospace. So engineering plastics, lower volume, very specialized application. Bioplastics. It's probably, bioplastics are probably one of the most confusing terms that can be applied. They are plastics derived from biological sources, such as plant-based materials. They can be biodegradable or non-biodegradable, and polylactic acid is one of those. Bio-based polyethylene is pretty interesting, right? Because in this scenario, the ethylene is derived from plants. However, it goes through a normal process and comes out as polyethylene. So it's nearly indistinguishable from other types of polyethylene. So other than a carbon-14 disbalance. You do have the biodegradable plastics. Again, here we'll see PLA. So you'll see this in some silverware that is being produced as biodegradable silverware. And so these should be broken down by natural processes such as composting or microbial activity. Environmentally friendly, but biodegradable is also a term that can be used quite variably, and there is home compostable biodegradable materials, and there are industrial compostable biodegradable materials. So it is another slightly confusing term, although I think it is something that we need to strive towards. The elastomers, you've got natural rubbers as well as synthetic rubbers. So styrene butadiene rubber, we've heard about the tire wear particles. And so this is the type of plastic or polymer that we are dealing with generally. In addition to the polymer, you have all the other components that are present in tires. But these obviously are flexible and resilient. We also have thermoset plastics. So these are the plastics that once heated, set to a firm and unchangeable material. So epoxies that maybe you mix the two components together into some of the epoxies, and they're used for adhesives. You can have polyester resins, and they're used in fiberglass and automotive parts, boat hulls. Polyurethane, which can be used for seals and gaskets and shock absorbers. Melamine formaldehyde, dinnerware. So some of these plastic plates that resemble the bamboo type plastics could be melamine formaldehyde. And then bakelite, which is probably the grandfather of plastics, one of the first synthesized polymers, and is used for electrical components, household items, and automotive parts, probably being phased out for the most part. But anyone that maybe has an old-fashioned phone at home or remembers growing up with one, those phones were often made out of bakelite. Thermoplastics, again, I have tried to capture some of the key polymers on here. But yesterday, after I sent in this presentation, I realized that I forgot one of the common ones, which is polystyrene. So that should also be on this list, but unfortunately it isn't. But what we do have is the low-density polyethylene and linear low-density polyethylene. These are used in the plastic bags, cling wrap, bubble wrap as common applications. Again, these are not exclusive uses. High-density polyethylene, if you have plastic milk jugs available, then that would probably be HDPE, cereal box liners, some piping, toys. And then there's polypropylene, which are yogurt containers, plastic lids, used a lot in automotive parts and medical applications. Polyethylene terephthalate, most common in your beverage bottles. So your Pepsi and Coke products are found often in PET. It's also used for other food packaging. And PET is the most common polymer used in polyester clothing. Again, not all polyester will be made from PET, but the majority will be. Polyvinyl chloride, PVC, pipes, flooring, and window frames. ABS, which are Lego bricks. So a lot of us have probably come across ABS polymers without knowing what they were. Polyamides, which is also nylon. Carpet fibers, also clothing. And polycarbonate, so compact discs, safety glasses, automotive parts. Now, polycarbonate, PVC, these are quite brittle, so you may actually see more microplastic formation from some of these brittles, or in a lab environment, they may be more easy to form. These top three, with the small asterisks, are collectively also known as polyolefins, because they are generated from an olefinic starting material, polyethylene from ethylene, polypropylene from propylene. These are slightly softer plastics, and in trying to generate microplastics in a lab, sometimes in the grinding, they actually get heated up, and then they will form long strings, which end up looking like a cotton candy or candy floss, and can make it difficult to generate some microplastics. And again, apologies for forgetting about polystyrene. Where are these plastics used? Here you can see on the left-hand side the global use of the polymers, and the European side on the right. Slightly different years, but what you can see are the trends are very similar. Packaging is one of the largest, use of plastics. Building and construction comes up in a close second, and then you have smaller uses across automotive, agriculture, and electrical and electronics. What type of plastic is being asked? In Europe, these are dominated by the polyolefins. So nearly half of the demand is polyolefin in Europe. And then you have smaller amounts of PVC, polyurethane, PET, polystyrene, thermosets, and then the big other thermoplastics. So clearly the thermoplastics are showing the dominant position in the use in Europe. Here is a nice like double matrix where you can see the types of the polymer across the bottom. And again, these first three are polyolefins, and then their use. So packaging is dominated by the polyolefins and the PET. Building and construction by PVC, both for its use in pipes as well as plastic window frames. And then automotive is probably dominated by polypropylene as well as some other thermosets. It's showing that we use a lot of plastics in our lives to make the things that we use. How do you select between all of these? Why would one plastic be in another? So polymer resin availability, I would say, is probably the biggest driver when it comes to the selection. Since a lot of them can be used for food packaging, whether you use polyethylene or polypropylene, they can be used interchangeably in some applications. The technical performance obviously is going to be a key driver. So PVC tends to be used for pipes of like the sewage or drainage type, and that tends to be non-replaceable. They are also PVC, you may know it because it's in blood bags, but it's being evaluated for other alternatives. Can we use other plastics safer to transport blood? The biggest driver also is polymer price. These plastics are relatively cheap and available. However, some applications are looking for the cheapest polymer type available for their end application. So price is unfortunately a big driver. And then what can frequently be interchanged on these? And what you'll see are polypropylene, polyethylene, nylon, ABS, polystyrene, PET, and PVC often have the ability to be interchanged in their application. One of the other issues that you need to deal with when you're thinking about the plastic that you have in your hand, things like shampoo bottles may not be made out of a single plastic. They may be made out of an outer layer and then a tie layer, which is basically something sticky in order to stick together a barrier layer with another tie layer, and you could have an abrasion or food contact. So, okay, in your shampoo bottle, it won't be food contact, but in other applications, it could be. So you may be dealing with 3 or 4 different polymer types in a multi-layer package. So we often are encountering many types of thermoplastics in our daily life.
Right, Eric, sorry,
Yes.
just to jump in, I know you're on your last few slides, but just to, if you could move through the next few quickly, just
Yep.
to leave a bit of time for the question and answers. Thanks.
Absolutely, yep. So plastic additives, again, here an additive is something that's added to the plastic and meant to be in the plastic. And there's a wide range that could be added, but they actually only represent a small portion of the total polymer. And here are some of the common additives that are given. So antioxidants, colorants, flame retardants, plasticizers. Not all of these will be present in all products. And generally, you'll see the plastics that have high additive content tend to be PVCs, ABS, nylon, polycarbonate. Moderate are the polyolefins and PET. And low or no content can also be polyethylene or polystyrene. And not all of these additives are present in all plastics. And again, this is a general overview. And with that, basically all the information here is without any claims on profit markets, this, that. It's a general disclaimer from my company. And if you are interested in us, you can also follow us on social media. So thank you for that. And with that, I will stop my share.
Perfect. Thank you very much, Eric. Thanks for sharing that perspective. Also very interesting. Okay, well, we have a little bit of time. I hope our panelists can stay for this section. So I'd invite any attendees to ask any questions. I see a couple of hands raised already. Perhaps just to move us in gently, we had a question put on the text. So I will ask Bernd if you had any suggestions for that to answer that one, please?
Now the question there, in a way, two parts. If we analyzed microplastics in tireware, so in my group, we are not doing any environmental analysis. We do simply predictions based on modeling. But there's the question whether tire is not fully plastic. In a way, that's the whole discussion is, should rubber be considered as a plastic? And that tires are now one of the examples we just heard in the last slide about these additives. A tire is just 50% rubber, the other 50% are additives. So it's, in a way, a tire is mostly additives that is driven around by a little bit of rubber. That's what you can say. So, and yes, what we know, some of these additives are highly toxic, or breakdown products of them are highly toxic. A lot of them have been under discussions for decades. The zinc, which is, it's a metal. There's a lot of zinc in tires, and the zinc in drainage and road unrough is toxic. They're polycyclic aromatic hydrocarbons. So there's a lot in tires that is, there it's clearly that is likely the actual problem, and it's not the rubber itself. The rubber is just the transport vehicle to bring additives, chemicals into the environment. So I think tireware, that's a clear example. The 50% is something else, and some of this something else is highly toxic and questionable. Then we need to talk. It's not the microplastic problem that is likely the main problem, but the additives. And yes, tire companies are now working on this. Now they are aware that they have a problem, and they work on this. What the solution is, that's something else, but they are aware that they have a problem.
Okay, great. Thank you very much for your thoughts on that one. Okay, I see a couple of hands up. I assume they've come up in order. So Lillian Cora, I'll pass over to you. Please, please put your question and state who you're asking it to. Thanks.
Now you can hear me. I understand. Yep. Thank you very much. As you know, I work in the area of health and environment, and nanomaterials in general, nanoplastics and others have been our worry for a long, long time. And my question here, after the presentations, is that in the fact we are facing a problem of environmental toxicity or toxic behavior by design, because we can find easily characteristics like persistence, that of course is a characteristic of the toxic chemicals, but also they are by design also performing activities. They are active, they are pollutants that continue performing the task for which they have been designed. By example, nobody mentioned the pharmaceuticals, but it's an important area, and it is pesticides. And in many cases, these nanoplastics continue being carriers of other chemicals to the tissues in the environment, but also they also facilitate the penetration of other chemicals in the living things. So I understand that we should be approaching the issue in a different way, not only at the end of the life being waste, even if the Basel Convention is focuses on waste, but reduction of waste, of toxic waste, it is important. Why don't we focus more in being sustainable by design in chemicals? Thank you very much.
Thank you, Lilian. Now, do any of the panelists have any thoughts on that, or?
Okay, I could.
Yeah,
or Eric,
well,
first.
Bernd, go ahead, and then Eric
Okay.
will pass to you. Yeah, thanks.
Yeah, you mentioned pharmaceuticals. Of course, they are a very specific group where some of these plastics may be used. And there are very specific ones used. And we have done in the nanoplastic modeling and release modeling, we have also looked at some of these, in a way, bio-nanomaterials, how you can call them. And some of them are containing polymers like PLGA. And there we have done some of these release models. But there it's important to see that a lot of them, they are degraded within the human body. That's one of their functionalities, that they are not excreted to a large extent. So there we have to be really careful, because these are very specific polymers. This is not PET what is injected there. These are very specific polymers that have to be biocompatible. And yes, they are designed to do some things in our body, but we cannot just compare them to something like PET or PVC. I think that's important. We need to then look at the specific polymer that is used. The same is for agriculture, where these are also very specific polymers.
Thank you, Eric.
Yeah, I was just going to address the last part of your comment question, Lilian, in the safe and sustainable by design, and that is something that industry is taking very seriously. As part of the ICCA work, that we are working on an additives database that will basically look at the additives and eventually to their breakdown products that will help basically in the circular economy and allow the materials to be used. So therefore, the safe and sustainable identification of polymers, of additives that will allow basically that circularity to happen is already being addressed and worked on. But again, it's not an easy solution, but it is already in our crosshairs to be worked on.
Okay, thank you very much. I see Jawahir Al-Fahud is also asking for the floor. I allow you to talk. Please unmute yourself and go ahead.
Hello, everyone. Thank you so much for, do you hear me?
Yes.
Thank you so much for this informative webinar. I have a question probably to Natalie for the research on nanomaterial, nanoplastic and microplastic and the additives that coming out of the plastic. We know that those chemicals and additives are already used in other material, not only plastic. So what makes plastic so special that all the focus now on the science community is only on plastic, although these material are existing in other, these additives and chemicals are existed in other material, which has even worse impact on the climate compared to the plastic. So why the focus on the plastic, and is there any way to mitigate these additives and chemicals across all materials, not only plastic, and possible like technical or analytical tools that will distinguish those additives coming, whether they are coming from plastic or other material? So please, if you can highlight on this, thank you so much.
Thank you for your question, Jawahir. It's a really interesting question, in fact. You know, I think you asked why the focus on plastics, and I think the reason is, I mean, it's in the public eye. We see it. It's everywhere. It's littering our environment, and because it's littering the environment, it's exposed to environmental stressors, UV radiation, abrasion, you know, cold and freezing and thawing in certain regions. And this can accelerate leaching of certain chemicals from the materials such as plastic. So I think that's definitely a motivation for us to understand how plastic acts excuse me, as a vehicle for these other additives to be introduced into the environment. So I hope that answers part of your question. And then your second part of your question, I'm sorry, can you remind me the second part of your question?
Whether the analytical tools are
Right.
accurate enough, to detect if these additives are coming from plastic specifically or other material.
Yeah, I mean, that's a really interesting question. Personally, I'm not an analytical chemist, so I can't say too much about that. And I'm not sure. I mean, I think if, you know, again, I don't want to speak as I'm not an analytical chemist, but I suppose that if you have certain molecules that are slightly different in composition from one that is used in a plastic, then you might be able to differentiate what the source of that additive is in the environment. But I don't know if Eric or Bernd, if you have more comments about these analytical techniques. I'm not an analytical chemist. I'm sorry, I can't say much more about that.
No, same as on my side. We just use very seldom some more simple analytical techniques or collaborate with other people. But definitely additives, this is a big question. And especially their importance. What is actually a particle effect and what is actually the effect of additives contained in particles? And the main problem, as usual, is the characterization. It's similar in the nano field. If we do not have characterized our plastics that we use in the research correctly, we never are sure what effect comes from the particles and what is from a very specific additive, because usually we just get it from somewhere and maybe there is something in that is highly toxic and we don't realize, and we assign it as microplastic toxicity, but in fact it's maybe the toxicity of a very specific additive that is known to be toxic. In some of these cases, in the early phase of the nanoplastic research, this has happened because some of these polystyrene nanobeads that are used, they contain a biocide to stabilize the suspension. So researchers did ecotox studies and they added also a biocide. Surely the organisms died, but this had nothing to do with the nanoplastic. It was just that there was sodium azide in there, which is, yes, a highly effective biocide. So when we did the meta-analysis, you have to screen out all those studies that use the polystyrene particles that contained sodium azide. It was a lot of detective work to find this out, but we were able to screen them all out. That's something we need to consider, these additives.
Okay, thank you very much, Shaw. I note we're about to go over time. I hope our experts can stay on a little bit longer, and I hope it's not too difficult for the participants. I propose to take one more question from the floor and then work through some of the Q&As before we finish up. So I have just the next in line, so I apologize to others, but so we had Fouad Abdulmogni. I'll allow you to talk and then please unmute yourself. Fouad?
Yes.
Yep.
Good evening.
Please go ahead.
Good evening. In the end, we conclude from the seminar the best way to drink water is use pottery vessels made of clay.
Okay, Fouad, do you have a specific question? Sorry. No. Okay. All right. Well, thanks for that. Sorry to others, but I think we should just move through the question and answers and then try and get everyone finished up for the day. Perhaps Bernd, it's most appropriate to you. There's one here on have you considered micro or nanoplastic present in the air?
I think that's a relatively new topic, that there is a lot of micro nanoplastic in air. It's important for our modeling transport through the air. And now there's more and more that it's like many of these persistent organic pollutants, there's a worldwide distribution through the air. There's no place on Earth that does not receive micro nanoplastics. So this is what we know. They're everywhere on the highest mountains. So it's definitely a topic where we will hear much more. It's the same problem of analyzing them at low concentration. You need to collect them. You need to be sure that you don't pollute your sample during analysis. But yes, we will hear much more about this diffuse pollution that we know now that affects the whole globe.
Okay, thank you. There's a question on presentations. Yes, we will share the ones we can. Afterwards, we will put a bit of information on our webpage and share it around along with the survey link afterwards that will come up. So we will we'll share what we can. We then have a question: are there any cell biological effects known about nanoplastics in cells, e.g. apoptosis, changing membrane properties, interfering with mitochondrial function? I don't know if any of our experts would be willing to respond on that one.
I can comment, Oliver, that as far as I know, I'm pretty sure there are studies. I can't think of them offhand right now, the name of the study, but I'm quite certain there are. So a quick literature search can probably identify those.
Maybe what I can add here, that a lot of the research on nanoparticle toxicity was actually done with polystyrene nanobeads. So a lot of the work for the last 15 years has been done with a very specific type of nanoplastic, which is now a problem for the nanoplastic field, that it's all about a very specific material that has no environmental relevance. But in fact, we know a lot about nanoplastics, and a lot of the nanotoxicology work is actually nanoplastic work. So we know a lot about these effects of particles on cells. And of course, they are different from those of metallic nanoparticles that can release ions. But yes, we know what are the nanospecific effects that these particles can have on cells.
Okay, thank you very much. I then see there is a question on what is the current global policy regarding the use of plastic. There are multiple discussions. So the Basel Convention has taken into account plastics as part of waste, but of course, there are discussions on a global treaty on plastics that is ongoing. Hopefully, we'll come to some form of finalization at the end of this year in the final INC in Busan, and so hopefully we will have a treaty in place for next year. We then have a question here from Lubna El Abed. My question concerns how we can replace single-use plastic with biodegradable plastic without competing with food safety, and how to remove chemicals from textiles without altering the quality of the fabric. A few different issues there, and probably beyond some of the science that we've been looking at today. I don't know if any of you would like to add some thoughts on that. Eric, was that something?
Yeah,
go for it.
I mean, I can add briefly, and it's not a super helpful answer. If it was easy, we would already do it. And so we know that there are a lot of challenges. There is a lot of research going into this area. However, as you say, there are a lot of competing interests that are going into this. We need food safety, we need applicability, we need functionality, and all of these need to come together. So if it was easy, we would have done it, but we're working on it, and I hope that we will get there soon. Sorry, it's kind of a non-answer, but it's the best that we have probably in the time.
Okay, thank you for trying. And yeah, well, it's proof that no matter how many experts we bring on, there's always a topic that we can't cover and not easy to solve. So that's fair enough. We then have our last one for today. We have Mansour Al-Aisei. I wonder if it's more for Natalie, but which one of the microbes can analyze nanoplastics as mentioned in the last presentation? Is that one you could answer, Natalie, or?
I wonder if it's related to Eric's presentation and maybe related to the biodegradation of the plastics, because it mentions microbes.
Okay.
And Could it be? Because otherwise I'm not quite sure what the question is asking.
Yeah. I mean, I'm not sure either as far as microbes being able to analyze nanoplastics. I mean, we do know that there is some work and some evidence that there are some microbial degradation of plastics. However, I'm not sure if that's the direction where it can be. So, and to be honest, off the top of my head, I don't know which one of those microbes is showing promise in being able to degrade plastics further. I don't know if Bernd has come across any of that in his continuum. So I'll stop.
Also, for me, it's unclear what the question really refers to. Of course, it's an important point. What happens to nanoplastics? Are they further degraded? Is it microbial degradation? Is it chemical degradation? Or are they just stable? If plastic gets smaller and smaller, then the question is, do nanoplastics also get smaller? And at the end, we just have monomers, and then they become part of natural organic matter. But I think that's an open research field. Yeah.
Okay, thank you very much. And all participants are encouraged to get in touch with us, and we'll try and sort of get you some further information, maybe contact the experts again, or see if we can help answer in another way. Of course, our survey also asks if there are new areas you'd like us to consider for subsequent webinars, and maybe that will help us direct the planning for that. I do note Anna Maria Vekic was asking for the floor. I think we haven't gone over by too much, and I think we're closing up. So Anna Maria, if you can be very concise and quick with your question, I think we could squeeze this one in. So Anna Maria, over to you to unmute yourself, and then we'll close up. Thanks. Anna Maria, are you able to unmute yourself?
Okay, sorry. I was asking for Eric. Eric, you mentioned that we have more safer plastics for blood package. So can you tell us some of them?
Yeah. So, I mean, what it is that it's being evaluated. So I typed an answer in the response in the Q&A, and I'm sorry if I misspoke. So there's ongoing research to find the alternatives, but to my awareness, there is no yet agreed upon alternative. So,
okay.
Sorry, hopefully that clarifies.
Thank you very much.
No.
Okay, thank you very much. All right, we will start closing up there. So on behalf of UNITAR, my colleague George Kaliganis, a senior advisor, would just like to say some closing words. So over to you, George.
Thank you very much, Oliver. Dear participants, my name is George Kaliganis, and I am a senior advisor at UNITAR. First of all, I would like to thank you for your participation in the webinar, and special thanks to our speakers, Bernd Nowak, Nathalie Tufenki, and Eric Rushton, for their great commitment and insightful presentations. They have invested a lot of time and energy in this event. Thanks to them, I hope that this webinar has contributed to an in-depth look into the world of plastics and also microplastics and nanoplastics. First up, we had a good overview of the life cycle of plastics. We have learned that model calculations of microplastic release are possible, and that car tire abrasion is quantitatively the most important part of microplastic and nanoplastic. We also heard that emissions to soil are quantitatively more important than emissions into water, and that abrasion of textiles produces a whole slew of different nanoparticles. Secondly, we also learned through studies on the aquatic organism Daphnia magna and the fly Drosophila melanogaster that it is possible to distinguish between different plastic polymers in the microscope. This is a great challenge. Natalie explained to us how it is possible to detect, localize, and identify unlabeled microplastics and nanoplastics using various microscopic techniques, such as open photothermal infrared spectroscopy combined with histological techniques. And our final presentation gave us an overview on plastic. We heard about the different classes of plastic and the typical applications of thermoplastic. We also learned that the largest proportion of plastic goes into packaging. The choice of polymer depends on the availability properties and price of the polymer. We have a survey to seek our feedback, and through this, we kindly request you to let us know if this webinar was useful and if you would like to have more webinars on related topics. And if so, please identify which particular topics would like us to address. Once again, many thanks to the speakers and thank you for your attention. And Oliver, please could you tell us if the PowerPoints will be available as PDFs? Over to you, Oliver.
Thank you very much, George. Yes, so thanks to all our participants today for making it and joining us. Thanks indeed very much to Bernd, Natalie, and Eric. Great to have you join us. Thanks for your collaboration. That was very useful. It's been a valuable second webinar in our series in collaboration with the BRS Secretariat. So we thank the Secretariat again for their work on this. We're trying to bring different perspectives, different stakeholders for this series. And today was very valuable that we were able to focus on micro and nanoplastics. As George mentions, there's a survey available. We would love to hear from you whether you enjoyed today's webinar, what topics you might like for future webinars as well. So there's a QR link here. The SurveyMonkey link is in the chat. And as I mentioned, we will send a follow-up message to this webinar that will contain the PowerPoints that we are able to share, the survey link as well. And we hope to carry on engaging with you on this topic. So for the last time from me, thank you very much. Thanks to our presenters. We hope you learned a lot today and we look forward to engaging with you all in the future. Thank you very much. Goodbye.